This session on the application of the rough path theory will bring together the presentation of the success stories of the signature-based methods in various applications, including the health-based handwritten character recognition and action recognition. So let's welcome the first speaker, Imanol Perez from University of Oxford, and he will present using signatures to predict ALS progression.
Yeah, thank you. Right. Thank you for the introduction. So medical data often comes in as sequential data. For example, typically one has access to a group of people, and for each of the individuals in the group, one has access to some sort of sequential data. For example, maybe a sequence of measurements taken for each of the individuals over a period of time, and the challenge is to see how to make sense out of that data. Moreover, typically obtaining this kind of data is quite expensive because it's, after all, medical data. So these data sets are very small, at least in machine learning standards, and it makes the whole problem even more challenging because now you have this high dimensional input, a stream of measurements, and you have a very small data set. So the challenge is to see how to extract the most useful information from the data, throw away the less informative parts of the data, and see whether you can tell something informative from the important things you've captured from the data set. So in this talk, I will discuss how you could use signatures for this purpose, and I will do it in particular applying it to try to predict the progression of amyotrophic lateral sclerosis, ALS, in the context of a competition that was organized a few years ago. So back in 2012, there was this competition. The objective of the competition is to see whether, if you're given some clinical trial data, whether you could predict what's going to be the progression of the disease on different individuals. This competition was actually it had a very significant impact, and it had a price of $50,000. So it was an important competition. More specifically, the challenge was the following. Using 3 months of clinical trial data, can we predict the progression of the disease in the next 9 months? As a result of the competition, this paper came out. So this is the paper that the organizers of the competition published. And this is actually a very interesting paper because, well, to begin with, they talked about the data a little bit. They talked about the challenge. They also talked about the methodology of the winning teams in the competition. But they also published the data, and they also published the predictions of the winning teams. So you could, at home, create your own model using the data. You could compare it with the predictions of the winning teams, and you could see how you would place yourself in the competition. So it can be used as a benchmark in a way. So it's actually quite interesting. So what was actually the data that the participants were given? So there were 2 types of data. The first type of data was static, so it was mainly demographic data, things like age, gender, and so on. So this is the data that didn't change throughout the period where the measurements were taken. But then there was the time evolving data. So things like blood pressure, weight, pulse, uric acid, phosphorus, and so on. So this was the challenging part of the data. So what were the challenges here? So first of all, this is time evolving, and there was actual information in the sequential nature of the data. It's not the same if you gain weight for those 3 months, or if you lose weight over that period of 3 months. So there is information in the sequential nature of the data. Also, different participants were taking different types of measurements. Maybe participant A got the blood pressure, the weight, and the phosphorus measured, whereas participant B had the weight, uric acid, and phosphorus measured. So you have different type of measurements for different patients. And also different patients got this measurements measured at a different number of times. Maybe one participant got the phosphorus checked 3 times, whereas another participant got it checked 5 times. So here the challenge is to see how you can put together all the data, extract the useful information, and make sense out of this data. So this was the biggest challenge of the competition. So I wanted to include like a machine learning pipeline that the winning teams followed in the competition. And it's actually a very standard pipeline that people follow in machine learning projects. So typically you would begin by processing and normalizing the data. In particular, they had to do things like dealing with missing values and then normalize the data and so on. Then you would extract the features. So once you have pre-processed the data, you have to say what's important from the data. So here, because of the challenges of the data I just mentioned, the participants they had to extract some ad hoc, data-dependent and handcrafted features from the data. Things like the minimum, the maximum of the measurements, the last measurement, the average value, and so on. They could do this because they had some prior knowledge about the data. They know that the last value could be something useful to make the prediction of the progression of the disease. They also knew that the minimum and the maximum value could also be informative to do the prediction and so on. So because they had a prior knowledge of the data, they could handcraft some of the features. Then once they had those features, they would plug it into some regressor model. So the popular choices were things like random forest, Bayesian trees, gradient boosting. And once they had that, they would obtain the predictions for the competition, and the organizers decided who was the winner by considering the root mean square deviation as the metric to compare participants. So this is essentially the pipeline that participants followed. So how we could use signatures in all of this? So first of all, signature is a sensible thing to use for this kind of data because, well, to begin with, it's an object. It's actually an infinite sequence, which was defined in earlier talks, that describes the path. This description is faithful, meaning that the signature of a path is unique, so that this description fully describes indeed the path. It also has some universal approximation theorems similar to neural networks, meaning that they can be used to approximate a rich enough class of functions. And also, as Hao described in her talk, you could take the logarithm of this object, and it turns out that this is a minimal set of information that still determines the signature. So you could even compress more the dimension of the original highly dimensional object. So therefore, this signature provides a data-independent way of extracting the features from stream data. And in particular, with signatures, we don't have to care about missing data, different number of observations, non-uniform sampling, etc. Because signatures get rid of the parameterization part of the path, so you don't care about these things. You just do not have to handle it in a special way because the signature already takes care of that in a very natural way. So therefore, if you want to extract features from stream data, the signature is something sensible that you can use. So here I wanted to include a few quotes from the paper that came out of the competition to show you that some of the difficulties that were mentioned in the paper are addressed in a very natural way by signatures. For example, in the paper, they mentioned that the remaining features were time resolved and could not therefore be incorporated directly into standard machine learning frameworks because time points and number of measurements varied between patients. So different patients had different number of measurements and types of measurements. With signatures, you just plug in the path into, you just compute the signature, it generates a vector of a fixed dimension for any patient, and now you can indeed use traditional machine learning regressors. So there's no problem with that. So teams had to convert each type of time resolved data per patient into a constant number of static features by applying various statistics. So they struggled to find some constant number of features that described the original path. Again, the signature does that automatically really, so you don't have to care about that it does it in a very natural way. Approach was to select designated measurements as features such as the minimum and maximum of the values. The latter approach was successfully applied by the best performing team. Notably, this approach is supposed to be robust. It's supposed to be robust, yeah. So again, because they had some prior knowledge, they know that the minimum value and the maximum value are going to be relevant to make the predictions, and they use that as features. The signature actually captures things like minimum and maximum of the path, the last value of the path, the average value of the path. So instead of trying to think what could be some relevant features, you may as well consider the signature, which already captures that, and you just can forget about handcrafted features. They use specific approaches for feature selection, missing value imputation, and so on. So again, you don't have to care about missing values with signatures, and you have a data-independent way of extracting features. So let's see now how the machine learning pipeline would be modified when you incorporate signatures. So we still have to normalize the data, but we don't have to deal with missing values now, but we still have to do some kind of normalization, as in all machine learning problems really. The only bit that is really modified is this bit. So before they would say, okay, what is important from the path, the minimum, maximum, last measurement, etc. Now we are using the log signature, so we don't need any specific knowledge about the data, because we can just apply the log signature and use that as the feature set. And once we have that, we would pass it into a regressor model. Nothing is changed here. We can use the same sort of models that they used in the competition. In particular, we used random forests. And we can now just take the predictions for the competition and see what we get. So the only thing that is really changed is the feature extraction part. The other thing can be left without being modified, so you can still use traditional machine learning methods. So these are the results from the competition. So these are the top 3 teams. As I said before, in the competition they use the root mean square deviation to decide who's the winner. So the smaller the better. But because they give the predictions, I included also 2 other metrics to make a more thorough comparison. In particular, I used the Pearson's R and the R squared. So here, the higher, the better. So if we use the log signature approach, it outperforms the other teams in all 3 categories. So we see that using this data-independent way of extracting features is already good enough to outperform these teams who decided to use the features they extracted the features in a very data-dependent way because they have some prior knowledge about the data. Also notice that the only thing that we change is really the way we extract the data. We also use a random forest, which was used by the winning team. Well, it's a popular choice across the teams. We use the same sort of analysis. The only fundamental change was in the choice of the features. That's the only change we made, really. That's all I wanted to talk about. Thank you.
Is there any question?
Could you talk in a little more detail about how you prepped your data for and applied it and then applied random forests? Just a bit more detail on that, please.
Yeah. So the data was a sequence of measurements taken for each of the patients. So it was something like, on this date, at this time, this patient got the phosphorus checked, and the value was this one. So you could construct a path in the following way. The path at any given time t is going to have a value which is the last measurement on each of the categories. So if the last measurement of phosphorus was yesterday, it's going to be that last value. If the weight was checked 1 week before, the value for that dimension is going to be the last value checked, which was 1 week before, and so on. So now that you have the path, you can construct the signature using the package that was the Python package that was discussed before, which converts that path into a vector of constant dimension, which you can be seen as the feature set for the original path. And then you plug that into the random forest. Sorry, Terry? Yeah.
One thing you probably slightly overstated is you said that they used expert knowledge and you didn't. Probably one area where you did is you did have to throw away several of the streams, didn't you, to keep the dimension of the whole problem under control?
Yeah. So there were lots and lots of measurements that were taken for different patients, like in total 38 possible measurements. So if you consider the 38 dimensional path and then you consider the signature, the dimension explodes. So you have to decide, okay, what measurements am I going to take? Well, I have no medical knowledge, so I don't know what things are relevant. So I said, well, I'm going to take the ones that were measured more often across the different patients. So I took like 10, 12, I can't remember how many. So I did introduce a decision over there, like how to pick the measurements that I'm going to include in the path. That is true, yeah.
So maybe time for one more question.
Yeah, so quickly just, is there a natural way of truncating the level at which you truncate the log signature? I mean, how did you decide on that?
Typically you would use cross-validation. So you would start with the level 1 signature, apply it on a validation set, do it again with the second order signature, and so on and so forth. And you would see that at the beginning you are underfitting, but in the end you will be overfitting because the dimension explodes, and somewhere in the middle should be the optimal order to be considered.
So let's thank Imanol again.